1, 2. Is that a good idea? I'm still not sure whether that's a good idea. Hi there, and welcome to Joku's Workbench. And welcome back to my CNC3040 video series. I am still sitting on a pile of parts that used to be a CNC machine and hopefully will turn back into a CNC machine. In this video, I will find out what to do with a shaft that is bent and with a bearing block that doesn't fit its bearings. This is one of the Y-axis bearing shafts of my machine. In my last video, I found out that the shaft is slightly bent by about 0.075 mm. The other Y-axis shaft is not straight either, but only by a bit. I need to test whether the bends will cause problems, for example with the bearings. For that, I place the shafts back in the machine and turn them in a way so that the high spots point sideways. Then I attach the bridge plate and the bearing blocks. I move the plate back and forth. To my surprise, the friction is quite constant everywhere, and I cannot feel any higher resistance in the middle where the high spots are. That tells me that either the side place in the bearings is too large to feel the high spots, or that the shafts simply flex a bit when the bearings roll over them. Both cases are not optimal. High bearing side play means that the bridge would move sideways under load or even tilt. And when the shafts flex, they are probably not rigid enough in the first place. In any case, I want the bent shaft to be straight. I measure the bending of my shaft at different positions and also mark out where the high spots are. The shaft is bent more or less evenly and in only one direction. That is good. A test with a file tells me that the steel is not hardened, so I should be able to bend it straight. I have already made a bending rig in my last video to get the bridge plate straight, and I will try to use it for the shaft. I place the shaft in the rig so that the middle is pushed down when I tighten the nuts. Then I start turning the nuts evenly. After some turns I hesitated. I already knew that my shafts might flex a bit under load, and before trying to get that one straight, I should really measure how much the shafts are flexing when the weight of the bridge and all the other stuff is pushing down on them. To measure that, I take off the rubber feet from my machine and put the frame flat on the table. I place a dial indicator on one of the shafts next to the bridge plate. Now I can see what happens when I add weight to the plate. This is 1 kilogram. And this is 2 kilograms. And this is 4. It looks like for each 2 kilos the shaft flexes by about 0.04 millimeter. The bearing blocks, the bridge and all the other parts that sit together on the Y-axis weigh about 8 kg. That weight is shared between both shafts, which means that each one of them gets about 4 kilos of load and flexes by about 0.08 millimeters when the bridge is in the middle. And that means when the shafts are straight, the tip of my tool would hang almost a tenth of a millimeter lower in the middle than at the edges. When I would place the shaft that is now bent more in the machine with the high spot pointing up, it would be nearly straight when the bridge pushes down in the middle, and the bend would basically compensate for the flexing under weight. And so what I should do instead of trying to get that shaft here straight is bending the other shaft to the same amount. I located the high spots of the other shaft and placed it in my bending rig, so that the bend is increased when I tighten the nuts. I did several rounds of careful bending and measuring. I got the shaft to 0.07 millimeters out of straight, which is more or less equal to the other one. I will stop bending here because I might make it worse again when I continue. I will measure later how precise the Z height of my machine is when I move it around, but that has to wait for another video. Speaking of precision, I never took a look at the lead screws. Hang on. What you see here spinning is the Y-axis lead screw. Yikes! I don't need a dial indicator to spot that this thing is not straight either. But for good scientific practice, I will measure anyway. I use a bit of cardboard in between the screw and the indicator so that the plunger is not affected by the threads. Yeah, that lead screw has more than a half millimeter difference between highest and lowest position. The screw is not hardened either, as another file test tells me, so I will try to bend it straight. It flexes quite easily actually, and I have to be extra careful. Instead of using my bending rig, I rest it on its ends and put my body weight on it very carefully. After some attempts, I got it into the ballpark of 0.1 millimeters out of straight. That is good enough, and I am done with bending for now. The second task for today's video is fixing the Z-axis bearing block that sits on the X-axis. It has two holes that house 4 LM16UU linear bearings. In my last video, I explained that the old bearings felt loose on the shafts and needed replacing, and that they were a pain to get out because they were essentially pressed into that block. This block is really puzzling me. The holes were drilled in the factory, obviously, but somehow they managed to make them too small, just by a bit, some hundredths of a millimeter maybe. And the person who has assembled the bearings into the block probably just used a hammer to get them in. After getting the bearings out, I sanded away the biggest burrs in the holes. I could probably continue sanding until the new bearings fit, but that would carry the risk of the holes losing their cylindrical shape. If that would happen, the new bearings would not be in line anymore. I need a grinding tool that removes material locally and controllable. Professionals use something like a master brake cylinder hone for that job, but I don't have one. I basically need some sort of grinding mandrel that would be attached to my drill and that holds a piece of sandpaper wound around it. And I could design it in CAD and then 3D print it. Before starting the design for 3D printing, I went through my random stuff box and found this plastic item. It has all the features that I need already and it has the right size. All I need to do is removing the screw and replacing it with an 8mm threaded rod as shaft. I cut out some narrow pieces of 240 grit sandpaper and wrap one around the mandrel. A piece of foam material gives me some springiness and pushes the sandpaper against the wall. Now I can start sanding, although aluminium is sticky and would clog up the sandpaper quickly, but I can avoid that by moving the whole procedure underwater. This is the first hole. I go back and forth with the sanding tool in the hole and regularly check in between how well the bearing fits now. This is the second hole. That one took a bit longer and more cycles of testing and sanding. But the small stream of metal chips in the water looks promising and oddly satisfying. At least now I have some magic pixie dust for which I need to find a fancy glass bottle. The sanding process worked great and now all 4 bearings are a good sliding fit in the holes. I put back the group screws and then test with 2 shafts how the blocks feel. It might not be visible on video, but that feels so much better than before. Nothing rattles and everything is rigid. Looks like I can finally start to put the machine back together. My next video will be short and simple. I will show a bit of the reassembly process and another small modification. See you next time.